Look, building machine learning models in a localized notebook environment, it's relatively straightforward. You know the drill. But transitioning those chaotic, duct-taped prototypes into a robust, enterprise-grade MLOps system, well, that is a completely different engineering beast. In this explainer, we're going to define the exact blueprint for building a production-ready assembly line for your machine learning models. We are going to transform them from fragile, one-off experiments into highly resilient, scalable software systems. Okay, let's dive into this. Here is a step-by-step roadmap we'll follow today. We'll start with the foundation of MLOps systems, jump into dataset management, design principles, talk about automating workflow orchestration, dig into metadata and artifact tracking, and finally bring the whole shebang together in the production-ready pipeline. All right, station number 1, the foundation of MLOps systems. Because honestly, you absolutely cannot build an enterprise-grade ML system without engineering a highly stable structural base long before a single model is ever deployed. To really understand why this foundation is so absolutely crucial, just look at the dependency chain of ML engineering. You literally can't just skip straight to automated machine learning at the very top. True MLOps only happens after you've nailed the lower levels. First, you have to master DevOps, which means rock-solid CI/CD pipelines and a serious containerization strategy. Then you've got to master data and platform automation, building out cloud infrastructure that can handle massive data throughput. Without those baseline operations, trying to automate machine learning is like trying to run a massive high-tech factory on a faulty electrical grid. It's just going to crash. Now, constructing that foundational architecture requires highly specialized talent across 3 main engineering roles. First up, data engineers. They build the continuous data ingestion and processing pipelines, heavily leaning on distributed frameworks like Apache Spark or streaming platforms like Kafka. Next, MLOps engineers. They manage the automation for creating datasets, training, and deployment. These folks practically live inside containerized ecosystems, orchestrating workloads with Kubernetes and Docker. And finally, system engineers, who build out the overarching ML infrastructure across cloud environments like AWS, GCP, or Azure. The magic happens when you merge these specific technical roles into one cohesive automated system, because that empowers your data scientists to independently own the problem, from initial research all the way to production. That brings us to part 2, dataset management design principles. Without an aggressively managed data pipeline, your entire assembly line is doomed to collapse, period. A dataset management service essentially acts as a highly specialized data gatekeeper. Functionally, it's ingesting raw, messy data from your data lakes, think AWS S3 or Google Cloud Storage, and systematically processing it into strictly structured training data. This structured layer, which usually lives in optimized SQL or NoSQL databases, outputs data that is ready to go, complete with validated examples, standardized labels, and explicit versioning. Basically, it guarantees your algorithms are consistently fed high-quality, reproducible fuel. So the crucial point is building an enterprise-grade dataset manager means sticking strictly to 5 non-negotiable rules. 1, dataset reproducibility. You absolutely need tools like DVC to recall exact historical data snapshots for troubleshooting. 2, a unified API across different data types. By using gRPC or REST endpoints, users interact with images the exact same way they interact with text, which clears up huge engineering bottlenecks. 3, strongly typed data schemas to validate incoming data so you don't get unexpected pipeline blowups. 4, internal scaling baked right into the storage layer to handle wildly varying dataset sizes. And 5, data persistency via immutable storage, meaning you never ever accidentally overwrite or lose critical training states. Now, why does all this matter? Well, enforcing these strict management principles gives you something called separation of concerns. Proper dataset management completely decouples your data engineering workflows from your model algorithm development. For enterprise scaling, this is an absolute must. It means your data engineers can refine pipelines while your model developers are optimizing algorithms at the exact same time. They're iterating in parallel, which dramatically speeds up the overall velocity of your projects. Now that our data is securely managed, we move to the next critical step. Part 3, automating workflow orchestration. At its core, orchestration runs on a directed acyclic graph, or a DAG. It's basically a mathematical map that explicitly dictates the sequence of your pipeline. It says, hey, task A has to finish successfully before tasks B and C are even allowed to start. In practice, these DAGs are written as infrastructure as code, usually Python, and pushed to version control. The second that code merges, it triggers the orchestrator to automatically spin up the necessary compute resources and execute every single task perfectly in order inside its own isolated environment. When it comes to picking an orchestrator, you're generally looking at two industry heavyweights, Apache Airflow and Kubeflow pipelines. Airflow is phenomenal if your team already has deep roots in existing ETL processes, strong Python skills for scheduling, and relies a lot on relational databases like Postgres. Kubeflow, on the other hand, is a beast for organizations heavily invested in cloud-native Kubernetes environments. It's laser-focused on container orchestration specifically tailored for the end-to-end machine learning lifecycle.
Regardless of the tool you pick, your orchestrator needs to hit 6 core design principles: criticality, usability, extensibility, task isolation, scaling, and human-centric design. Let's focus on task isolation for a second, because in an enterprise setting, it is paramount. It means executing every single step within its own temporary Docker container. By isolating tasks like this, if there's a resource leak during a heavy data processing step, it doesn't crash the entire pipeline. If a step fails, the orchestrator just spins up a new container and retries that precise step. Simple, clean, and highly resilient.
We are now entering the Systems Memory Center. Part 4, Metadata and Artifact Tracking. Because let's face it, a beautifully orchestrated pipeline is functionally useless if you can't trace exactly how a model was built when something inevitably goes wrong. Now, what's really interesting here is how the metadata store serves as the foundational hub of the entire ecosystem. It has to be highly available, seamlessly connecting your experimental pipelines, your automated production workflows, and your prediction services. It basically captures a holistic view of the system state, logging every output and configuration from developers, data scientists, and system engineers into one centralized registry. The primary job of this hub is to establish comprehensive model lineage. Think of lineage as this incredibly detailed, traceable web that maps any deployed model straight back to its exact training run, the precise dataset version it saw, and the specific git commit hash that birthed it. If your monitoring systems trigger a 3 a.m. alert because a production model's accuracy just tanked, model lineage is your best friend. It lets your team instantly see when the model was produced, what data it trained on, and the hyperparameters used, so you can debug the issue immediately. To get that perfect lineage, we have to meticulously track two different things: artifacts and metadata. Artifacts are your actual, tangible files, compiled models, inference code, massive static datasets. Those usually live in object storage like Amazon S3. Metadata, though, describes those artifacts. It's the training duration, the accuracy metrics, the name of the engineer who triggered the run. That goes into relational databases. By hooking up tools like MLflow or weights and biases into your DAGs, you completely automate the logging of both. Okay, let's move to the final stage. Part 5, the production-ready pipeline, where we synthesize everything into a fully automated loop that actually serves customers. At this point, the finished assembly line operates as one continuous loop. Data ingestion triggers validation, usually using tools like Great Expectations, to make sure the data isn't garbage. That validated data flows right into pre-processing, maybe using TensorFlow extended. That feeds directly into model training and rigorous mathematical evaluation. Once it clears the validation thresholds, boom, the pipeline automatically pushes the model to deployment via TensorFlow serving or Torch serve. And remember, every single step here is orchestrated autonomously and logged straight into that metadata store we just talked about. But getting a model out of the lab and into that continuous loop, that takes some serious engineering heavy lifting. We call it the productionization blueprint. First, prototyping code must be ruthlessly refactored into production-quality software. Every component must be Dockerized for portability. You absolutely need CI/CD in place to trigger automated testing the second someone merges code. Model inputs and outputs have to be strictly versioned. The models themselves need to be deployed behind robust APIs, like FastAPI for inference. And finally, you have to continuously monitor for data drift. And deployment is definitely not the finish line. The final absolute must-have requirement is closing the feedback loop. You need observability tools, Prometheus, Grafana, Evidently AI, constantly capturing live performance metrics and checking for statistical data drift. When the live data starts drifting away from what the model originally trained on, these tools automatically tell the orchestrator to spin up a new pipeline run and retrain the model on fresh data. Because an enterprise ML system isn't static, it's a living organism that needs continuous monitoring and autonomous retraining to stay accurate. Which leaves us with the ultimate engineering test. You've built the models, but have you built the system that lets them survive? I highly encourage you to look at your current architecture today. Those brilliant, highly optimized algorithms literally hold zero business value if they're trapped in a Jupyter notebook. Without a robust, automated MLOps infrastructure to manage data, orchestrate isolated tasks, and meticulously track metadata, those models are just not going to survive the chaos of a production environment. Thanks so much for joining me for this explainer, and I look forward to exploring our next technical deep dive together.